Have you ever tried to build one of those ridiculously complex Lego sets? Okay, now imagine doing it in zero gravity. And the pieces are the size of a school bus, and they get delivered one at a time by rocket. Well, that's pretty much the story of the International Space Station, the single largest thing humanity has ever built in space. So how in the world did we pull it off? Let's dive in.
First, let's just try to get our heads around the sheer scale of this thing. The finished station weighs in at 460 tons. I mean, to put that into perspective, that's like 300 cars. And there's no rocket on Earth that can launch all of that at once. Every single part had to be sent up into orbit, piece by painstaking piece. And here's where it gets really mind-bending. This entire construction site, it wasn't sitting still. The whole time, it was whipping around the planet at 17,500 miles an hour. That means it orbited the entire Earth every 90 minutes. So this wasn't just building something, it was like a high-speed ballet in orbit.
So that really brings us to the core question, doesn't it? How do you even begin to assemble something the size of a football field in the complete vacuum of space, dealing with wild temperature swings and radiation, all while moving at orbital velocity?
Well, the first massive hurdle wasn't just what they were going to build. It was simply how to get all the pieces there in the first place. This was the logistics problem. And honestly, it was a monster of a challenge.
The answer to that problem, the real workhorse of this whole operation, was the space shuttle. You know, for a huge part of its career, the shuttle's main job was basically being the galaxy's most expensive delivery truck and construction platform for the ISS. It flew more than 40 assembly missions, hauling these gigantic modules up in its payload bay. But just look at that cost. $10,000 to get a single pound into orbit. Every launch was just this monumental and monumentally expensive effort.
Okay, so you did it. You launched a multi-ton module into orbit. Great! But now you're staring down an even trickier problem, one that was part engineering and, part global politics. This was the compatibility problem.
And this slide just lays it out perfectly. See, the ISS was this huge collaboration mainly between the US and Russia, who were, not that long ago, Cold War rivals. Their engineering philosophies were totally different. The Russian modules used round hatches with their docking system, the US side used square hatches with a completely different mechanism. They were just fundamentally not designed to connect. It's like trying to plug a European power cord into an American wall socket.
The solution was this really elegant, clever piece of engineering called the pressurized mating adapter, or PMA. And that travel adapter analogy is literally what it is. It's a universal translator for space hardware. It's a cone-shaped adapter that has a Russian-style round hatch on one end and an American-style square one on the other. A pretty simple concept, really, but it was an absolutely critical piece of hardware that made the whole station possible.
And this all came together in December 1998 on mission STS-88. I mean, this was the moment of truth. The Space Shuttle Endeavour flew up carrying the American Unity module, and it had these all-important PMA adapters already attached. Once they got into orbit, the shuttle's big robotic arm reached out and very, very gently grabbed hold of the Russian Zarya module, which was already flying on its own. Then, using these tiny, precise thruster firings, the shuttle brought them closer and closer until, click, the latch is engaged. And right there, the International Space Station was officially born.
Okay, so the pieces are in orbit, and we have a way to connect them. But that brings up the next big question. How do you actually do it? How do you move and connect these multi-ton modules with the precision of a surgeon, all while floating in zero gravity?
Well, the heavy lifting was mostly done by a robotic workforce. First, there was the shuttle's own 50-foot arm, the Canadarm. But the real star of the show was Canadarm2, the station's own bigger, more powerful robotic arm. The coolest thing about Canadarm2 is that it can actually walk. It can detach one end, swing over, and connect to a different grapple point on the station, moving end over end like a giant inchworm. These arms were the construction cranes of the whole project.
But having all that power meant you had to be incredibly delicate. As Jared Owen points out in his amazing video on this, every move was this slow, high-stakes procedure. It wasn't like just swinging a crane around. Moving a brand new module out of the shuttle's bay and lining it up perfectly could take hours of these tiny, careful movements, just to make sure nothing got damaged.
And of course, for all their power, the robots couldn't do everything. For all the really intricate stuff, tightening the final bolts, connecting miles of power and data cables, installing antennas, for that, you needed the human touch. And that meant astronauts had to go outside on spacewalks, or extravehicular activities, EVAs. These were absolutely critical to bringing the station to life.
So the station is getting bigger. The external structure is really starting to take shape. But, a bunch of connected metal cans is not a home. So the final, and maybe most important phase, was solving the livability problem. How do you turn this construction site into a place where people can actually live and work, permanently?
This timeline really tells that story perfectly. You see, it starts in '98 as just this empty, uninhabited outpost. The real game changer was in 2000 when the Russian Zvezda module arrived. That's the one that had the crucial life support systems, air, water, all of it. And right after that, the very first crew moved in, starting an unbroken streak of human presence in space that's still going today. Then, with the Destiny Lab and the Quest airlock, it went from being just a habitat to a world-class scientific laboratory.
And getting its very own airlock? That was a huge deal. It meant the station was finally self-sufficient for spacewalks. They didn't need a shuttle docked anymore. The whole process is just wild to think about. After hours of suiting up, they pump all the air out of the chamber until it's a vacuum. Then they open the outer hatch. And because that hatch faces straight down, the very first thing an astronaut sees when they go outside is the entire planet just hanging there in space below them.
So really, when you step back and look at it, the ISS is so much more than just an amazing piece of engineering. It's a symbol. It's a blueprint for what can happen when countries, even former rivals, decide to work together on something peaceful and ambitious. It's this floating, shining testament to what human ingenuity can accomplish when faced with seemingly impossible odds.
And that's its true legacy, right? The lessons we learned building this city in the sky are literally the foundation for everything that comes next. The ISS proved that, yes, we can build and sustain a human neighborhood in orbit. So the question it leaves us with is a really exciting one. Now that we know how to do that, what incredible things are we going to build next? On the Moon, on Mars, and beyond?